the moment of inertia of the bottom flange about neutral axis, and that is nothing but moment of inertia of the bottom flange about an axis passing through its CG or centroid plus AH square, that is A1 multiplied by distance of its CG from the neutral axis. Now we know that the moment of inertia of the bottom flange about its own axis, x is equal to 1 by 12 BD cube, 1 by 12 160 into 40 cube, plus area, that is 160 into 40, that is 6400 multiplied by h square, and that is nothing but 90.60 minus 40 by 2, that is 20 and whole square, and we achieve this is the value of I1. I wish you have understood now how to find out the value of I1, as I have discussed one of the problem in this particular previous problem. Next, I2. I2 is the moment of inertia of the web about neutral axis. It is nothing but moment of inertia of web about an axis passing through its CG plus A2 into distance of its CG from neutral axis square, AH square. Now, so first one is the moment of inertia of the wave about an axis passing through its CG. It is nothing but 1 by 12 BD cube. If you are referring the figure previously, this is our B, that is of 20, D is of 200, so 1 by 12, 20 into 200 cube. See the plus area, that is the 200 into 20, 4000 multiplied by AH square. Now what is that? That is nothing but the CG of the second is over here at this particular point, and it is distance from this CG of the second area to this neutral axis. So this is my H2, and that is nothing but 140 minus 90.66 square, and we achieve the value of I2. If you want to refer the same thing how it has been achieved, please refer in this particular table top. The given section is of like this. This is the given section. We found out the neutral axis like this. Now this is the first part, second part, third part. The second part is known as web. CG is acting over here, its own CG of second part. This will be my H2. What is that? This available total from CG is of 200 by 2 plus 40, as this is 40, this is of 200, so this is of 140. From distance of neutral axis to the bottom fiber, and that we found out as it 90.66. So this distance is nothing but this minus this, and we found out the value of H2. Now next, I3 is the moment of inertia of the topper flange about neutral axis, that is moment of inertia of topper flange about an axis passing through its CG plus A3 into H3 square, that is the distance of CG from the neutral axis square. Now what is the moment of inertia of top flange about an axis passing through its CG? That is 1 by 12 BD cube, referring the previous figure. 1 by 12, B available is 80, D is 20 cube. 1 by 12, 80 into 20 cube, that is the first part, plus area into H square. Area is 80 into 20, that is 1600. It is over here, into H3 square. Let us see over here on this table top. What is H3 square? Now if you are referring This is the total depth. See, this is my CG of this distance. If we are referring the distance from the CG of the third part from the bottom face is 40 plus 200 plus 20 by 2, that is 250. 250 is the distance from the CG of the third part to the bottom flange. Now the CG distance is known to us, that is 90.66. So the available, this one is our H3, and that is H3 is equal to 250 minus 90.66. Now let us come to this on PPT. See the things. 250 minus 90.66 whole square, we achieve this as the I3. So I is equal to the I1, that is the contribution of moment of inertia from the first rectangle bottom flange, plus I2 contribution of the moment of inertia from the web, and third is the I3, that is the contribution from the top flange, and we did the summation, we got this much value as the value of I for this given I unsymmetrical I section. Now for a simply supported beam, the tensile stress will be at the extreme bottom fiber and compressive stress at the extreme top fiber. This statement is very much important. Let us be understood what is the meaning of the statement. Let us use the tabletop. Simply supported beam, which is given to this in this particular problem. Length is of 5 meter. So for any kind of the loading, maybe the UDL, maybe the point load, any kind of the loading for the simply supported beam, the nature of bending moment is of sagging. The sagging means top is under compression and bottom is under tensile stresses. So development of the tensile stresses at the bottom. So in our problem, the constraint is which is given to that is of maximum tensile stress developed in this particular section is of 20 megapascal. Means if the stress is beyond 20 megapascal, my beam will be fail. That is the meaning of the statement. Means to find out the load, I have to use this maximum tensile stress that is developed because of the bottom fiber. Means this I have to use the Y maximum, not I have to use, but I have to use the YB, Y bottom, as the given constraint is of maximum tensile stress. So for the maximum tensile stress at Y, it is interesting, the maximum tensile stress is given, that is developed at the bottom fiber, and as its bottom fiber I have to use YB, that is 90.66, distance of the extreme bottom fiber, that is when the tensile stress is maximum. Now if we use the basic relationship M over I is equal to F over Y, and then M is equal to F over Y into I. F is given to you, that is 20 Newton per mm square megapascal, divide by Y 90.66, multiply by I that we have found out. We found out there is some value of moment 213,00389.85 Newton into millimeter. Let us give it this equation number 1. because our aim is not to find out the value of m, our intention is to find out what will be the UDL which will safely act on our beam. To find out the UDL safely, let W is the uniformly distributed load in Newton per meter on this simply supported beam. Now, because of the uniformly distributed load, the maximum bending moment at the center is WL square by 8. What does it mean? Let us come on this particular tabletop. So, given beam is this one. If this is my W in Newton per meter, then definitely the reaction which is of, this is L is the length, W into L by 2, W into L by 2. Maximum bending moment developed at the center is equal to WL by 2 into L by 2 distance minus W into L into W into, I have to find out the moment over here. So, W into L by 2 into half of L by 2, and you simplify, we achieve is it is as WL square by 8. So, we achieve on this tabletop this is our reaction. We found out maximum bending moment is of WL square by 8, which is developed, if this I will plot the bending moment diagram, which is developed at the center, that is WL square by 8, and is equal to the m. This answer is known to me. So, if we come to this particular PPT, we know that answer. So, m is equal to W into 5 square divided by 8 into Newton into meter, which is equal to W into 5 square 25 multiplied by 1000 divided by 8. Why it is 1000? To convert Newton into meter in terms of Newton into millimeter, I found out it is 3125 W Newton into mm. This is 2 number. Now, if we equate equation number 1 previous case, what is moment? If you are referring, the m is this answer number 1, and from this equation number 2, this is our answer. If we equate these two things, that is 3125W is equal to 2130038.9.85, we get W is equal to 6816.125 Newton per meter. This is the answer of W. Now, once we found out the value of W, our intention, that is the next step, is to find out maximum compressive stress that is developed. Now, the given section, the beam which is of simply supported beam. At the simply supported beam, the bottom fibers are subjected to the tensile stresses while the top fibers are subjected to the compressive stresses due to the sagging nature of the bending moment. Now, if we are considering here the 20 Newton per mm square, that is the maximum tensile stress developed at the bottom which is given to us, our intention is to find out maximum compressive stress that is developed at the top. To find out that, I have to find out YT, that is 169.34 mm, because the compressive stresses will be developed on the top fiber. M known to us, I known to us. So, F is equal to maximum compressive stress. So, using basic relationship, M over I is equal to F over Y. Replacing F is equal to M by Y into Y, M divided by into Y, M known to us, I known to us, Y is nothing but YT top, 169.34 we achieve, it is 37.36 Newton per mm square. So, from today's session, we have understood how we can simplify our problem in case of the unsymmetrical section by using the concept of center of gravity. So in the today's session we have discussed the problems of unsymmetrical section. In the next session we will more discuss about the unsymmetrical section and the problems related to the strength of section. So I kindly request you to solve more numericals at your room. Thank you.